Now, being evil, mean and nasty, most people, when they're looking at arithmetic progressions, and remember they can ask you for the proof of the arithmetic progression formally, but most people actually know that the sum of an arithmetic, or the particular term in an arithmetic progression, if you like, is given by a plus n minus 1d, and the sum to n terms is given by n over 2, 2a plus n minus 1d. And what most people forget, or don't ever actually realize, is that this means that, which means that a rather different way of doing this would be to approach it by n over 2a plus l, where a is your first term and al is your last term, because in this particular case I know the last term is 71. So these questions typically involve you forming a pair of simultaneous equations, but if you know this Gaussian approach to it, and if you want to do a little bit of research, look at Carl Friedrich Gauss. Very, very clever man, and in fact all this mathematics is Gaussian mathematics. Allegedly he upset his maths teacher by being so good that he could answer all the problems that his teacher set him. But you're going to have to research that one. I'm going to use that in this particular case because it's a sneaky little trick, because I know that the sum of my numbers, and I know that I've got 7 numbers, so I know clearly that n is 7. I'm not in this particular question going to prove these particular formulae, and I know that my sum to n terms, sum of 7 terms, is going to be 329, and I know that T7 is a plus 7 minus 1 times d. Alright, so I would normally expect, if I was using the classic ones, to have to form a simultaneous equation in a and d and solve those simultaneously, but in this particular case, if I use this little beauty, I know that 329 is going to be 7 over 2 a plus 71, because I know that the last term is 71. Okay, so that gives me, and I don't like the fact that, I could put 3.5a if I wanted to, but it would be easier to simply double both sides. So 658 over 7 minus 71 is equal to a, which implies that a is 23, which makes life really easy. I'm going to shift onto another screen because I've got the space to do that. So I've got that my last term T7 was equal to 71. I know that a is now 23, and I know that the 7th term was a plus 6d, so therefore I've got 71 is equal to a plus 6d, and seeing as I know a is 23, 71 is equal to 23 plus 6d, which quite happily gives me that d is equal to 8. Now at that point, lots and lots and lots of people would put their pens down and say, I've solved the simultaneous equations, or I found A and D, therefore I found the two things I need. Read the question. Dachlan a question. All right, because it wants the 7 numbers. So in this particular case, you have got to, there's my first term. Adding 8 gives me 31 last time I checked, plus another 8, 39, 47, 55. Almost made a mistake there, little brain doesn't work sometimes when you're doing simple things. 71. There is my answer. But I would only have gained all the marks if I'd taken the trouble to read the question. Okay, so you've got to think about how to do these things. Try and find a way of doing them easily. Just because it's A-level maths, just because it's pure mathematics, doesn't mean you have to find a hard way of doing it. The whole beauty of mathematics is if you know short, simple steps, use them.
Slightly oddly, the solution you've just been shown is not in the mark scheme. That doesn't mean it's wrong, obviously it's right, but the mark scheme uses the method mentioned in what you've just watched of using the formula Sn equals n over 2, 2a plus n minus 1d. So the two formula used in the mark scheme solution, so this is an alternative way of doing it, use that sum formula and obviously the term formula, so un is a plus n minus 1d. So because we have S7, the sum of the 7 numbers, so that's 329, 329 is, n is 7 because it's the 7th one. We don't know a, 7 take away 1 is 6, so we've left with 6d, and we know that the 7th term is 71, so here we have 71 is a plus 6d. And if we tidy this up, we can cancel the 2 with that 2 and make that 6 into a 3. We can divide by 7, and that then leaves us with a plus 3d equals 47. So 329 divided by 7 is 47. We also have a plus 6d is 71. That means we can subtract these. So if that's equation 1 and that's equation 2, we do equation 2 take away equation 1, and that leaves us with 3d equals 24. Divide by 3 gives us d equals 8, and then sub that back in and we get a plus 3 times 8 is 47. 3 8s are 24, subtract that, and that leaves us with a equals 23. And so that's a way of doing it using the, if you like, standard formulae. But notice that both formulae are given in the formula book should you need to check. And probably worth having a look, because that might have reminded you of the half n a plus l version, which is a quicker solution, as you've seen here. We're just going to have a quick look at the proof of the sum of the arithmetic series. Gauss was mentioned earlier on, and the story involves him having to add up the numbers from 1 to 100. I'm going to show you a quick way of doing that, and the good thing about seeing this, which you may well have seen before, is it reminds you of the method for the proof. So if we want to add up the numbers from 1 to 100, we write them out. and then we write them backwards. And you'll see that each pair adds up to 101. Now, if we call the first line sum of 100 and the second line sum up to 100, then the third line is 2 times the sum up to 100. Therefore, 2 of the sum up to 100 is equal to 101 times 100, because there are 100 of these additions. So, the sum of 100 is 101 times 100 over 2, which is 101 times 50, which is 5050. So, with that in mind, how do we work out the sum for an abstract arithmetic series? So this is deriving the formula, or proving that the formula is what it says on the formula book. Then we would say that the sum of the first n terms is the first term plus the second term plus the third term, and then all the way up to the third to last, the second to last, and the last term. Now I'm doing it the same way as I did in green. You don't necessarily have to have as many of those written out yourselves, but it links it to the numerical version above. So if we now write that backwards, we get A plus D, A plus 2D, plus plus A plus n minus 3D, A plus n minus 2D, and A plus n minus 1D. And I never leave quite enough space at that end for those, but never mind, we've just about squeezed them in. And that then gives us 2 times the sum is 2a plus n minus 1d plus, now this one also adds up to that because we've got n minus 2d plus another d, so that gives us 2a plus n minus 1d. And then, to save myself time, should have some adds in there, we'll put the same at this end, so 2a plus n minus 1d plus 2a plus n minus 1d. And now we have n terms, so we have n times 2a plus n minus 1d, and then when we divide by 2 we have the familiar n over 2 times 2a plus n minus 1d. And then, as it shows in the video, we can say that that equals n over 2 times a plus n minus 1d. And actually we sort of see that in this sum here. That final one is, of course, the last term. So this gives us n over 2 a plus l. And there we are. And you need to be able to reproduce that. They could ask for it in an exam, and it's a nice little bit of math to know anyway.